And this is lab 2, where we look at lines of charge. In this lab, we use tape to observe the transfer of electrons and use data collected to calculate the charge on the tape. And rather than treating the charge on the tape as point charge, we will distribute the charge evenly. And the results are that the charged tapes repel each other and that the magnitude of electric force was 1.16 e to the negative 3 newtons. The magnitude of gravitational force was 1.99 e to the negative 3 newtons. The fundamental physics principles at hand were Coulomb's law, where the electric force equals Coulomb's constant times charge 1 times charge 2, all divided by the distance between the two charges, as well as Newton's second law, where F equals ma. In the initial conditions, we had a piece of tape that was a length of 0.2 meters, a width of 0.019 meters, and a mass of 2.0 e to the negative 4 kilograms. And the distance between the tapes were 0.025 meters. Our observations were that the U-tape was ripped off the base of the tape, the U-tape attracted the hand, and a negatively charged pencil attracted the tape. Therefore, because it attracted the negatively charged pencil, the tape is positively charged. And we also noticed that when we had the first U-tape A and U-tape B next to each other, they repelled each other. Therefore, we set our system as U-tape B and our surroundings as U-tape A, and we created our model this way in order to measure the electric field force and force of gravity, using D as our main measure between the two forces. And we use that in our computational model, where we use the distance between the two tapes as our R equals observation location minus charge particle position, and put it all in the electric field equation. And we also use the gravitational force equation and put them all in the computational model to observe what the two charged tapes would look like. And as you can see, the electric force is a little bit less than the gravitational force. Essentially, these two models should be the same magnitude. However, there is some discrepancies, which we'll get to in a moment. Possibilities of error were that some charge was lost due to handling. Therefore, our model wasn't super accurate from the observations and data we gathered. But another big issue could be that the distance between the tape was not measured accurately. In the model, if you decrease the force by a lot, it says that the force is infinite, and if you increase it by a lot, it says your force is very minimal. So not having a accurate D distance between the two charges would create a very big discrepancy. So since we measured it with the measuring tape, it wasn't super accurate, therefore our model wasn't accurate. Some similarities were that they were in the same magnitude, so that's good. That's a good sign that we're at least on the right track. Now, what if you had modeled each of your tapes as a single point charge like in the previous lab? Well, the electric charge would have been one magnitude larger, as we saw in the last lab. Therefore, that model is not super accurate. Now, why do these estimates differ? And which values are more likely to be close to the real value, and why? Since the line charge model is a sum of multiple point charges, it is a more accurate calculation than treating the length of the tape as one point charge. So, in conclusion, line charge helps better estimate the charge of objects. Point charges can be helpful, but they're not super accurate. Thank you.